Good morning, students from Erode Sengunthar Engineering College. AICTE PRERANA scheme for preparing SC and ST students for higher education. 8. Here, now I am discussing about the subject Chemical Reaction Engineering 1, and under the topic of interpretation of chemical kinetics. So myself, Aatral G.V., working as assistant professor in the Department of Chemical Engineering, Erode Sengunthar Engineering College, Perundurai. So before the topic, how to know that is what is the chemical kinetics, and from chemical kinetics means that is from which reactions or some others from which from is the materials to do the kinetic studies, how to clear understand. Okay, from molecularity level or process level or reactions levels. So among the three combined, it's going to happen the reaction. So from the reactions we are going to determine under the chemical kinetics, under the kinetics. So from the kinetic studies only we are able to identify, that is we are able to determine the chemical rate of reactions, like from in depth we can say order of reaction, molecularity of reactions, yield, conversion, we can say in other determined forms. Okay, so um, before the kinetic studies, we have to keep in clear that is reaction. Okay, so in reaction means all of you know for any manufacturing or any productions. Okay, so here in manufacturing or any production means from n number of manufacturing or n number of production is there. So from acid to base, whatever may be. For example, from sulfuric acid also we can take as in production of sulfuric acid, here applicable for both. That is the unit operation and the unit process can be involved. Okay, so in unit process means uh, so from this production, unit operation and unit process, we have to keep in clear two things. That is unit operation means that is physical changes can be taken place. Okay, so and then in unit process, chemical changes can be occurring. So from these chemical changes we call as process. Okay, so from any manufacturing, it's have unit process also involved. Unit process also. So from unit process, we can tell in change of chemical reactions. Okay, so in here reactions, that is we have to clear reactants product. In between the reactants and product, we have to mention the temperature, pressure, catalytic or non-catalytic. Okay, so and then the mode of reactions can be carried out under reversible manner or irreversible manner. Okay, so based on this is the basic concept from reactions. Okay, so in reaction we can classify it in many ways, like exothermic reaction, endothermic reaction, reversible, irreversible, catalytic reaction, non-catalytic reaction, homogeneous reaction, heterogeneous reaction, and then the reactions in series and parallel. So we can classify under the reaction in various forms. Okay, so from reaction here we have to mention how we can mention in terms of chemical kinetics means while the left and right we call as reactants. So for example, we can take an as ammonia manufacturing, ammonia production. So in ammonia production, So in ammonia production, for example, we can take as the reactant nitrogen and hydrogen. So here the reactant nitrogen and hydrogen means we can mention that is 2 moles of nitrogen and then plus 3 moles of hydrogen. So in bracket we can mention the aroma. So we have to represent the temperature, pressure and catalyst also. So after the reaction, the chemical changes can be obtained. That is the forms 2 moles of ammonia. Okay. So here with the reactants, that is the nitrogen molecules and the hydrogen molecules can be consumptioned. That is, it can be disappearance to form the appearance of ammonia molecules. Okay, so this is the concept involved in the reactions. Okay, so after that from these reactions, so they can be after these reactions we can mention like a rate of reaction. We have to uh, define the rate of reaction. That is, we have to define the rate of reaction means. So the rate of reactions that is we giving the reactant that is changing. What is changing here? So moles. So in other words, we can say and technically concentration. So that is change in concentration with respect to time. So therefore, the rate of reactions can be proportionality to dCA by dt, that is change in concentration with respect to time. Okay, so next we have to simplify it into minus RA equal to K into CA. Okay, here the rate of reaction we can indicating the rate of reaction minus RA. So here minus Y we are here indicating this, that is the disappearance of the product to appearance of the, sorry, disappearance of the reactant um, to appearance the product. Okay, so that is the minus RA equal to finally equal to K into CA. So all of you know that is the minus RA equal to rate of reactions, and then K is rate constant, and the CA equal to concentration of this reactant. Okay, so here the constant value how to determine, that is the rate constant, and then here the CA concentration term we have some the powers. Okay, so that's why the sum of the power of the concentrations. Okay, so that is called the order of reaction. So here they specified in this slide, they are the four important factors which affect the rate of reactions. That is the rate of reaction. What are the affecting terms? Factor affecting. The first one, reactant concentration. Second one, temperature. Third one, that is the dosage of the catalyst. The action of catalyst is, that is dosage of the catalyst, and then from surface area, and then that is the catalyst behavior surface area. Okay. So here, basically from reaction, the further reaction we have to develop the kinetic studies means we have to see the main molecularity level. That is the molecularity level means suppose if any molecule have the depend upon various valency tendency. Okay, so based on the tendency, it can be exiting or not exiting. So that is the we have to understood, that is chemical reaction at the molecular level. For example, ammonia we have the valence 2 plus 3 plus means, so up to the valency level 3 plus 2 plus the ion particle can be exit. After over the 2 plus 3 plus valence means it's never involving. Okay, so that is here indicating at the molecularity level. Okay, so next one reaction rate means that is speed of a chemical reaction. Okay, that is how much amount of the speed can be carried out. How we can measure? That is in terms of concentration with the time. Okay, here the concentration also can be changed, depends upon the time. So that's why here speed of a chemical reaction is measured by the change in concentration with time. Okay. So the reaction is A gives B. Okay. So A gives B. This is the reaction. We have to measure in terms of two waves. Okay. The first one is speed at which the reactant disappear. Okay. That is, for example, here the reactant is A. So the reactant how much can be disappearing? How much speed can be, or in terms of how much moles can be disappearing? Okay. And second one, um, the speed at which the product appears. Okay, that is the we listen here. The reactions can be. We have to focus the calculate, measured, determined under two ways. We have to focus to one in reactant side, reactant part, or otherwise product wise. Okay, so that is why here they mentioned under two ways of measuring the rate of reactions. Okay, so the speed at which the reactant disappear first one, and the second one the speed at which the product appears. Okay, and then next already I told the reactions can be in mode of directions, either it can be in reversible or irreversible. Okay, so suppose the reactions can be reversible. Okay, so the reaction can be is reversible means suppose the product can accumulate and again back into reactants. Okay, so this is the reversible and irreversible vice versa. Okay, so here the rate of the rate of reaction can be totally dependent upon the how much amount of the reactant can be occurring. So here how much amount of reactant means here for example in terms of we can say the reactant can be in terms of moles like um, 2 moles, 3 moles of some other molecules. For example, 2 moles of hydrogens, 2 moles of sulfate particles. Like so, that is the rate of reaction can wholly depend upon only the reactants. Okay, and then how we can measure the rate of reaction? Okay, so in terms of changing concentration with respect to time. So how we can write? That is the rate equal to change in concentration with respect to time. Okay. So here, for example, in terms of graphical and in terms of example, we can have. So here C4H9 chloro in chloro aqueous form, chloroform, and then a water is in liquid form. So finally, this is the reactant. Okay, C4H9Cl. Okay, this is in aqueous form, and the water is in liquid, and the reaction can be represented in reversible forms. Okay, so the reversible forms it can relating the in alcohol aqueous form, that is C4H9OH. So remaining the acid can be releasing under the that is a byproduct or under releasing under the aqueous mode. Okay, so here it determined the reaction, and this reaction itself we can easily find out the that is the rate of reaction can be decreasing with the time. Okay, so here in graphical form also is shown. That is in x-axis time and then y-axis the molarity levels. In terms of we can take on as molarity level. Okay, so C4H9 Cl in aqueous form molarity level. So from this graph, that is the rate of reaction decreases with time. Okay, so and then so next one for another example, nitrogen pentoxide. Okay, so here nitrogen pentoxide, that is the one reactant. It gives liberating the nitrogen dioxide and oxygen. Okay, so here that is the for every 1 mole of oxygen that appears. Okay, so from reactant and side and the product side, here 1 mole of oxygen can be occurs. Okay, but uh, here the product can be 4 moles of nitrogen dioxide can be appear. Okay, so here it's indicating the overall reaction can be twice as twice of the nitrogen dioxide. That is nitrogen pentoxide. It's having the twice of the nitrogen dioxide. Okay. So and then after that twice of the nitrogen dioxide plus oxide can be in disappearing forms. Okay. So this is the reaction nitrogen pentoxide reaction can be indicating. So from this reaction also it means the changes in concentration of the reactant and the product is change in concentration of the reactant and the product is with respect to time. Okay, so we can write in terms of rate of reaction is that is rate equal to here how much nitrogen pentoxide moles is the 2 moles. Okay, so 2 moles means we can write in terms of minus because here minus y here indicating means this is the reactant. Okay, so if this N2O5 only disappearance to form the NO2. Okay, so that is why here indicating the negative term. Okay, here the rate equal to minus 1 by 2, that is 2 moles of nitrogen pentoxide. So that is why here minus 1 by 2 change in changing that nitrogen pentoxide, right? So N2O5 divided by del T. So del T indicating the change in time. So we write for reactant side alone. So we have to write product side also. So here minus this is the product. Finally, the product can be in appearance form. So 1 by 4 changing nitrogen dioxide by changing time, like change in oxide O2 divided by del T. Okay. So like from example here we consider as nitrogen pentoxide. For normal, for general reaction means that is small a capital A plus small b capital B gives small c capital C plus small d capital D. So like we have to write, that is in terms of before while we write nitrogen pentoxide like us, we have to write this general equation. So we have to see that in reactant side we have to mention the negative sign, and in product we doesn't care about the negative signs. Okay, so this is the main thing. And then next one, next topic, rate law. Okay, here the rate law. Okay, so how final the expression for rate law? So in generally the rate of reactions. So from before these slides we saw a lot of examples: hydrogen pentoxide reactions, and then general reaction, and then C4 HCl. Okay, so from based on many examples of reactions, so in generally we can say the rate of reaction. Okay, so that is the rate of reaction increases as concentration with increasing the time. Okay, so in other ways we can say the rate of reaction can increase in concentration in the reactant of molecules. Okay, so that is the reactant of molecules can be in pollution, can be more occurring. Okay, that is the pollution of these molecules can be occurred in increased form. So we can say in two main factors. The first one is the rate of reaction increases as concentration increases in time. Okay, or else we can say the rate of reaction increases as concentration increases. That is, in reactant we have more number of reactants. Pollution occurring between the reactants. Okay. So finally, the overall based on the overall rate of reaction can be given in form of rate law or rate expressions. That is the overall concentrations. That is the overall concentration. How much amount of the concentration in moles that in dependent in rate of reaction, that is we can call as rate law or rate expression. Okay, so this is the definition form, and mathematical how we can say. So the general reaction, that is A gives B. Okay, so the rate here the rate equal to K into the component A and the component B. Here the moles power, the number of moles can be represented in terms of powers, that is m, small m, and represent small n. Okay, so here the capital in this mathematical rate law. So the capital A and B represent the reactants, and the exponential of small m and n are called the reaction orders, and they K equal to proportionality constant or rate constant, and then the overall reaction order. Okay, so the overall reaction order means how we can say the how we can define the order of chemical reactions. That is the sum of the power of the concentration terms we called as order of reaction. Okay, so here one example for ammonium in aqueous form, and the nitrogen dioxide also in aqueous form. But the basic nature can be ammonium in aqueous form is in positive ions, the NO2 in it's also in aqueous form, but it's in negative ion form. Okay, so from this following reaction, ammonium and nitrogen dioxide both are in aqueous form. This is the reactants. Okay, so finally the product can be give nitrogen and water. Okay, so here the reactants can occur can will giving the both same phase, aqueous phase, but the product here occurred here. The nitrogen can in gas phases and the water is in liquid. Okay, so here because from this reaction the ammonium, that is NH4 plus, it means the rate, finally the rate of reactions so doubles with nitrogen dioxide. Okay, So or otherwise we say the nitrogen dioxide can be doubles the rate of reaction can be doubles with ammonium constant. Okay, so uh, here the rate of reaction we say that is two waves, that is the changing of the rate of reaction with increasing in concentration with increasing in time, or otherwise known as the rate of reaction with increasing in concentration with increasing the collision occurring in reactant. Okay, so here the third wave how they are denoting here means that is in means of ions, that is plus and negative. Okay, so suppose when you are giving the reactant in terms of ions form. Okay, so based on the ion form, either the negative ion can initiate the doubling the rate of reaction, or negative ions can initiating the double of the rate of reactions. Okay, so this is the third form. Okay, so here the rate of this reaction can be expressed as, okay, how we can write, that is rate equal to K into ammonium, that is Na4 plus into NO2 minus. Okay, so generally the reaction is said to be first order. So based on the ions. So here based on the ions alone, here it doesn't involving any balancing or any powers. So that is why here the reaction is said to be first order. But how we can say the overall order of the reaction is second order. Okay, so here order of fractions. So order of fraction means that is sum of the power of the concentration terms. Okay, so a reaction, first one here indicating a reaction is zero order in a reactant if the change in concentration the reactant produce no effect. Yeah, obviously, because if in reactants also any changes doesn't occurs, that is any changes means that is concentration does not change. Does not change means dependent on the reactant. Okay, so any changes doesn't occur, that is we can say zeroth order. Okay, so and then first one second one first order. Okay, how we can say first order means suppose the concentration can be doubled. Okay, so the concentration term can be doubled means here the rate of reaction also can be doubling. Okay, and then suppose it is second order means doubling concentration can be doubled, but the rate of reaction here doesn't double. Okay, so here it can be caused quadruple. Okay, and then third order. Okay, so here third order means that is here also concentration can be doubling. It leads to the 8 times of the rate of reactions. Okay, so from based on these zeroth order, first order, second order, and third order, the rate constant value, that is the rate constant K, does not depend upon the concentration term. We have to keep clear. Okay, so does not depend upon the concentration. So from these basics, we have to keep in mind to determine, we have to determine the rate law and the rate constant based upon the initial reaction rates and final concentrations. Okay, So after then we have to determine the first order, second order, and the third order, zeroth order. Before that, how we can change the concentration with time also we have to. Okay. So here the change of concentration with time means, so that is to convert the rate law into a convenient equation in the function of time. Okay. So in the function of time and then driving force as in terms of concentration to give concentration. That is if any reaction, that reaction can be converted in rate law. Okay. So from the rate law, how we can give in terms of concentration as function of time. Okay. So here first, for example, here first order reaction. Okay. So here first order reaction is, that is here indicating the term ln of a into suffix t equal to minus kt by ln of a naught. So that is at here indicating the concentration of component, that is reactant A after the reaction can be stopped at the end of the reaction, we can say. Okay, that is a y here representing the t. Okay, and k is all of you know, that is the rate constant, and t is time, and the a naught here indicating the initial concentration of the product at initially, that is the time equal to 0 at initially concentration of the time, initial concentration of the reactant A. Okay, so this is the basic terms for first order. So in graphical form, how we can plot means, that is in x-axis time and then y-axis ln of A by t. Okay, so in terms of slope equal to k. Okay, that is the tangent line is slope equal to k, and then the intercepting line we can say initial concentration, that is a naught value. Okay, so before we see first order reaction, and now we discussing about the second order reaction. So plotting the graph and all same, but the rate expression can be here varying. So in second order reaction means, that is 1 by AT, that is AT means after completing the reaction, indicating the small t. Okay, so equal to KT into 1 by A naught. So remaining and all same, the denoting terms and all same, but here the this term is considered for second order reaction, that is 1 by AT equal to K into KT plus 1 by A naught. So AT here indicating the concentration of A after some time. So and K equal to weight constant and T equal to time in second, A not equal to initial concentration of A. So here by plotting the graph, here the y-axis is 1t, that is time, and x-axis here time, and the y-axis the initial of reactant. Okay, so intercept only the initial of reactant means, that is 1 by A naught at the initial concentration, and the y-axis we have to product in terms of product means that is after completing the reaction, that is 1 by AT. Okay, so the intercept line can, at the starting of intercept we can identified 1 by A naught, that is initial. Okay, so and then the intercept line we can calculate the based on the slope. So that slope value we can say as rate constant. Okay, so and then after for zeroth order. Okay, so first one we saw first order, second order, and next one zeroth order. Okay, so here zeroth order, the rate expression itself rate equal to k into a naught. So here doesn't the reactance can be any changes, doesn't changes, does not take places. Okay, so that's why the rate equal to k. Okay, so next based on the k term we can write in terms of order of reaction is that is A of T equal to K minus, here the minus indicating is it doesn't involve any changes. Okay, so that's why here indicating the minus. Okay, so K into T plus A naught. Okay, so AT equal to concentration of A after completing the time of reaction, and k equal to rate constant, t equal to time, and a naught equal to initial concentration. So based on here we have to plot in of zeroth order reaction, that is x-axis time and the y-axis AT, that is the final, and then here the intercept line we have a naught initial concentration, and the slope based on the slope we calculating the k value rate constant, but in zeroth order the rate constant value is minus. So from we see the zeroth order, first order, and the second order. So next one that is the off-life period. Okay, so off-life period means here the off-life is the time that is for any reactions it can be taken the the reaction times for from original to half of the values. From original to half of the values means suppose the reaction can be stored, will hold the reaction can be carried out under 3 hours means for example the off life period can be, that is the it can be carried out under 1.5 hours. So the off life period can denoting the T off. Okay, so it's always denoting the T off. Okay, so like half-life period also we have to see first order process, second order process, and a zeroth order process. Okay, so here first one the first order process means the half-life T of how we can write means that is the T of equal to minus ln of that is the change in concentration. We can represent as of like means 1 by 2. Okay, so by rate constant. So the ln of 1 by 2 that is 0.5 equal to 0.693. So here therefore the first order in half life period, that is the D of equal to 0.693 by K. Okay, so here the K equal to rate constant. So like in second order reaction and zeroth order reactions. Okay, so for second order reaction means that is the half life the half life depends upon the reactant concentration. So for second order or any orders, generally we can denote T of equal to half life period. Okay, so therefore the T of equal to for first second order 1 by K by initial of initial concentration of the reactant, that is A. Okay, so like in zeroth order means where T of equal to initial concentration of reactant divided by 2 rate constant. Okay, so based on the rate of reactions, we have several theories. Uh, Organist theory, like pollution theory, molecular pollution theory, and based on the molecules, and then second one based on orbitals. Okay, so here that based on theories, the rate of reactions can be first one. Based on the theories only, they have set up into the model. Okay, so here the first one pollution model. Okay, so here the pollution model, because why here involved the theories, Arrhenius theory, pollution theory, energy theories, and then molecularity theories. Means basically while we are carrying out the reactions, always we under considered as the in reaction, in particular reaction, the temperature can be carried out under a constant manner. Okay, so but practically it's not, because in every reaction you can mention based upon the production and based upon the manufacturing. Suppose the um, product, suppose the reaction can be carried out under from this temperature to under this temperature. Suppose it can be carried out high temperature or low temperature or medium temperature. So here based on these temperatures, okay, so the temperature can be in increasing manner. Okay, from reactions. So from increasing the temperatures, so that's why here in based on the temperature only, here involving the theories like pollution theory, organic theory, and molecularity theory. Okay, so here molecularity theory means suppose if one molecule is there, for example copper. Okay, so here copper have state. Two state means that is two type of valence state. Okay, like 2 plus 3 plus like. Okay, so based on the state level, based on the orbitality state level, and based on the energy level, it can be transformed. Okay, that is the molecularity level. Okay, so that is pollution model, that is pollution theory means depends upon the energy levels, whether it can be easily collide with pollution with some other molecules or not. Suppose the molecules can be easily collided, it does not react. So these are the properties we have to see. Okay, the basic thing here in pollution theory, the molecules can be in easy to collide and react. Okay, so from pollutions, suppose the properties, which are the properties we have to focus means, suppose if any molecules can have high porosity, okay, so that molecules can be have high pollution factor. Okay, so here based on these various theories only, they framed pollution model. Okay, so the pollution model can be focused upon temperatures. Okay, so here, for example, they give me food spoiled. Food spoiled means suppose if refrigeration can play an important, if the refrigerant also it's main of in factor of temperatures. Okay, so and then next one the rate law equation. So here the rate law, rate of reactions, uh, not muchly depend upon the temperatures. Okay. So in collision model, assumptions can be made, like four assumptions. What are the four assumptions? Means for why the assumption can be made means that is the molecules in order of molecules can be in reactable forms. Okay, so the four assumption means the first one is the greater number of collisions faster the rate of reactions. That is how much number of molecules how much number of molecules can be collision occurred at first, the rate of reaction also at first depend upon the rate of reaction also. And then second one, the number of collision based upon the number of molecules, which molecule it's depend upon, which molecules can be present in the reactions. So the molecules present in the reactions basically depend upon the collision rate also varying, and then a rate of reaction also varying. Okay, so the second assumption. And then third one, suppose the rate of reaction can be carried out under high temperature. Higher the temperature means, so it's for higher temperature it need to carry out more energy. Okay, so more energy, and then more energy in the molecules, and then faster the rate of reactions. So this is the third assumptions. Okay, and then fourth assumptions. Suppose the molecules can be suppose the molecules can be going to collide into another molecules means, so it can releasing the small fraction of collisions. So that small fraction of collision also major part will lead to product. Okay, will lead to product. So these are all the four basic assumptions. So the first one, number of collision faster the, so the number of collision faster the rate of reactions. And the second one, the number of collisions depends upon the molecules only. So based on the depends upon the molecules only, uh, whether increases the collision and the rate of reaction also increased. Okay, third one, while employing the higher temperature, uh, it need a high amount of energy in rate of reactions. It need a high amount of energy for uh, stability to enhance the reaction in molecules. Okay, and then fourth one, suppose the molecules can be lead to collision. Okay, so the molecules in collision forms, so it can be, in fact, it can be released small fraction of collisions. So the small fraction of collision also lead to form a product. Okay, so next one, orientation factor. So here the orientation factor can how we can involve means, suppose the reaction of molecules can the reaction of molecules must be in colloidal form. Okay, so must be in colloidal form means we can say that is the molecules can have correct orientations. Okay, that is the correct orientation means it's depend upon the ions. In other words, balancing. Okay, so and then energy level. Okay, so suppose every molecules, each the molecules will have colloidals and orientation and have with good energy. So then only to form the products. Okay, so this is the here the orientation factor can be involving. So here from this orientation factor we can determine the effective collision and the ineffective collision can be identified. Okay, For example, here chlorine Cl plus NOCl. Okay. So from here it releasing NO plus chloride Cl2. Okay. The reactant. So the reactant is Cl plus NOCl. It gives NO plus Cl2. Okay. So here this reaction can possible as um, carried out under collision under in two factor rule, effective collision and ineffective collision. Okay, so the first one pictorial shown as effective collision. Okay, so here effective collision means before the collision as same for effective and ineffective. Okay, at the collision factor also is same, but after the collision it doesn't involve any other um, any other. It can be combined to the two molecules. Okay, so after the collision also it combined to the two molecules. Okay, so here based on the valency level, suppose the molecules does not carry out. Okay, so that is the will lead to ineffective collision. Okay, so next one, activation energy. How activation energy term can be involving the their activation energy term. How we can involve means suppose a reaction a chemical reaction. Okay, so in a chemical reaction it can changes or initiate any action. So initiating purpose we need any energy. So that energy, that is the minimum amount of energy we can say as activation energy. Okay, so that is a minimum amount of energy means suppose for example any compound have single bond, double bond, depends upon the bond. So we have to break the bond levels. Then only the modifying the structures, modifying enter into the reaction, enter into convert into next. So that is why uh, obviously need the energy. That is minimum amount of the energy is called as activation energy. Okay. So the activation energy can be denoted as EA. So based on the activation energy also varying the reactions. So for example, based on the activation energy, so methyl isonitrile. This is the example form. So here the methyl isonitrile, here indicating the varying the bond structures, varying the bond structures, and depends upon the chemical positions. Okay, so the first one H3C and N triple bond C. Here the indicating the double point. So the double point is shown under the reactions. Okay. So show under the reactions we have turned into C triple bond N. Okay. So that is the bond can be bend. Okay. So bends until the bond breaks, and finally it can be converted into CN bond. That is perpendicular to the portion is perpendicular to the methyl group portion. Okay. So this is called as activated complex of transition state. So in structure doesn't any happen. That is the bond in terms of chemical bonding, it doesn't happen. but the molecules of the position can be change, changing. So that is called the activated complex of transition state. Okay, so here the energy required for echo and a break is known as activation energy. Okay, so here in graphical form it shown as based on effect of temperature. That is effect of temperature means in terms of energy. Okay, so in x-axis reaction pathway and then here energy. Okay, so it can be in that is the activation energy under the change in energy. So here the activated complex can be occurred the maximum at the point. Okay. Okay, so from point of activation energy, here the mode of reaction is also very important. That is, suppose the reaction is in forward or reverse word. Suppose the reaction in forward means it's in exothermic and the reverse means in endothermic. Okay, so the example methyl isonitrile. From the example, the molecule needs to gain enough energy to overcome the activation energy barrier. Okay, so this graph shows the temperature and versus the energy of activation. So the kinetic energy and the fraction of molecules. Suppose the fraction of collision also lead to form product. Okay. So in terms of two part, minimum energy needed to your action. That is the activation energy. Minimum energy there depends upon the activation energy. The fraction of molecules based upon in terms of higher energy and lower temperature and higher temperature can be varied out. So from these two peaks, when the reaction can be carried out under lower temperature, it gives high stability and a high conversion factor when compared to the high temperature. So this is the from this graph, the point focused, the low optimizes low energy, low temperature level. It doesn't optimize the higher temperature. Okay. So next enter into molecule mechanism of reactions. So from this mechanism of reactions, based upon two category, elementary and molecularity. So elementary it can be deals upon a single step. That molecularity it doesn't like single step. So it involving number of molecules. Okay, it involving number of molecules means one molecular, two molecular, three. Suppose carried out one molecule means unimolecular we can say. Two molecules means bimolecular and three molecules means third molecular. Okay. So, but how many molecules can be involved but carried out under in elementary steps? Okay. So, for example, unimolecular means the chemical reaction we can write A gives B. So, rate equal to K into A. Bimolecular means A plus product gives product means rate equal to K into A square. Okay. So, after then and otherwise bimolecular means A plus B product and here A power 2 can write as 2 moles that is A and B. So A into B. Like trimolecular means also it can be varying either a triple A or double A plus B or A B C gives product. So by varying these reactants here the rate law also can vary. So in mechanism we can say like initiation, propagation, and termination. So in initiation, propagation, and termination, whether the three mechanism can lead to in slow step or fast step. Okay, so okay, um, okay, thank you. So remaining from based on these topics, we can see problems. Okay, so we discussed the topics from next class. Under the topics, we discussed the problems. Okay, thank you.